Hello, this is Lab 5 where we examine the motion of a slinky. The purpose of this lab was to extract the motion data of a falling slinky and to analyze how gravity, tension, and drag force affect it. A computational model was created and compared to the experimental model from Tracker. The computational and observed model had overall similar results, though their graphs did slightly differ. Key concepts for this lab include Newton's second law, which states that the net force is found from change in momentum over time. This is also the total of all forces acting on the system, such as the gravitational force, which is negative mass times acceleration due to gravity, and j hat, the unit vector. In addition, the drag force is the negative proportionality constant used times velocity squared and the velocity unit vector. The proportionality constant is the magnitude of the drag force, so it affects how much air resistance a system has. The higher the constant is, the more air resistance an object has. Finally, the position and velocity update formulas are from the second law. In the video analyzed, the system is slinky while the surroundings are everything else, such as the air and ground. The estimated calibration length for the slinky in the video analysis is 1.5 meters using the height measurement of the host. The mass of the slinky was estimated to be 0.2 kilograms based on recorded results found. While the slinky is stretched, tension and gravitational forces act on the system. Once the slinky compresses, drag and gravitational forces act on the system. The data points are tracked at the bottom end of the slinky, so the graph shows a plateau until the slinky compresses. As stated, the mass of the system was 0.2 kilograms. The slinky's initial position was negative 0.078 in the x position, 0.0335 in the y position, and 0 in the z position. The initial velocity was 0 meters per second since it started from rest. J hat was the unit vector for the positive y position, and the drag force proportionality constant was used based on trial and error. When time is less than 5.27 seconds, the bottom of the slinky is motionless. For this part of the code, the gravitational and tension forces are calculated using the formulas mentioned earlier and summed up to get the net force. Next, the velocity and position are updated from the net force. Now, when time is greater than 5.27 seconds but less than 8.53 seconds, both the top and the bottom of the slinky fall. Again, we calculate the forces acting on the system. Instead of tension, the drag force is calculated and added with the gravitational force because the slinky is no longer stretched but compressed. Once again, we use the net force found to update the position and velocity of the system and create the computational model. Possible errors in the lab are due to human error in Tracker causing outlier points in the observed model. In addition, as stated, the proportionality constant of the drag force was used based on estimation, so there could be more suited values. Based on the results, both models have similar outline shapes. The graphs plateau until 5.27 seconds, then decrease rapidly. While the observed model has a shaky slope due to inconsistent tracking errors, the computational model has a perfect slope, so it is evidently more accurate. The bottom of the slinky remains motionless because the tension from the stretched slinky counters the gravitational force pull, meaning the bottom is at equilibrium. Once the slinky compresses, the whole system falls together and the drag force acts on the system instead of the tension. Due to the slinky's weight, there is little drag force compared to objects such as paper balls that have more air resistance. If a slinky is horizontally stretched, gravity has no effect. Instead, a horizontal force is applied, such as hitting the slinky with a block. As seen in the demonstration, the right end of the slinky is motionless until the left end reaches it. The results are the same because tension is present in both scenarios. Thank you so much for watching.